Hello everyone. In this video, we will be discussing infinite limits and limits at infinity. To recall, let A be any real number. The definition of infinite limits, we say that the limit of some function f of x as x approaches A is equal to positive infinity if the value of f of x increases without bound as it gets closer and closer to A. And the limit of that function as x approaches A is equal to negative infinity if the value of f of x decreases without bound as it gets closer and closer to A. Also note that x approaches A can be replaced by x approaches A from the right or x approaches A from the left. So the definition of vertical asymptote, we say that the line x is equal to A is a vertical asymptote of the graph of a function f if the limit of that function as x approaches A from the right is equal to positive or negative infinity, or the limit of that function as x approaches A from the left is equal to positive or negative infinity. For the theorems, let f of x is equal to c be an element of all real numbers as x approaches A, and the limit of another function g of x as x approaches A be equal to 0. So suppose c is greater than 0 or a positive number. If g of x as approaches 0 from the right as x approaches A, then the limit of f of x all over g of x as x approaches A be equal to positive infinity. If g of x approaches 0 from the left as x approaches A, then the limit of f of x all over g of x as x approaches A is equal to negative infinity. It makes sense naman kasi if c is greater than 0, then the limit of f of x as x approaches A is a positive number. So this numerator would be a positive number. Then if g of x approaches 0 from the right as x approaches A, so the limit of g of x as x approaches A would be 0 from the right, so positive numbers then. So if the numerator is a constant, so a constant number A, and the denominator approaches 0 from the positive numbers, so you can expect that the value of the ratio would be approaching positive infinity. So if the denominator approaches 0 from the negative numbers, so you can expect that the ratio would be approaching negative infinity as x approaches A. So suppose c is less than 0 or a negative number, and g of x approaches 0 from the right, from the positive numbers as x approaches A, then the limit of f of x all over g of x as x approaches A is equal to negative infinity. So this is just the opposite of number 1. Yeah. So let's see any real number. Then for the first column, if the limit of f of x as x approaches A, for example, is c, and the limit of g of x as x approaches A is positive infinity, then the limit of the sum of f of x and g of x as x approaches A is positive infinity, and the difference would be negative infinity. The limit of the difference of f of x and g of x as x approaches A would be negative infinity. So you can just refer to this table to get the limit of the sum of f of x and g of x as x approaches A if the limit of individual functions is positive or negative infinity. For the third theorem, let c be any real number. So Again, if the limit of f of x as x approaches a, for example, is a positive number, so c is greater than 0, and the limit of g of x as x approaches a is positive or negative infinity, then the limit of the product of f of x and g of x as x approaches a is equal to positive or negative infinity. So the same logic applies to the succeeding rows. So you can just refer to this table to get the limit of the product of two functions as x approaches a. So the definition of limits at infinity, let L be any real number. So we can say that the limit of f of x as x approaches infinity is equal to L if the values of f of x gets closer and closer to L as x increases without bound. And the limit of f of x as x approaches negative infinity is equal to L if the values of f of x gets closer and closer to L as x decreases without bound. So for the definition of horizontal asymptote, we say that the line y is equal to L is a horizontal asymptote of the graph of a function f if the limit of f as x approaches positive infinity is equal to L, or the limit of f as x approaches negative infinity is equal to L. So you can visualize that using this graph. So for example, this is x and this is y. So, and there's a value L here. So this y value is L. So as x approaches positive infinity, the value of f approaches L. So you can consider this as a horizontal asymptote. So similarly, for vertical asymptotes, you can visualize that using this. For example, this is x and this is y, and there's a value a. So there's a value a here. So as x approaches a, from the left, the limit approaches, or the value of the function approaches positive infinity. So that's just one case. So you can consider this line x is equal to a as a vertical asymptote. So for the fourth theorem, let's see L1 and L2 be element of real numbers. Suppose the limit of f of x as x approaches positive or negative infinity be equal to L1, and the limit of g of x as x approaches positive or negative infinity be equal to L2, and the limit of a third function h of x as x approaches positive or negative infinity be equal to positive or negative infinity. Then the limit of the sum of f of x, the sum or difference of f of x and g of x as x approaches positive or negative infinity is equal to the sum or difference of the individual limits L1 and L2. So for the product, the limit of the product of f of x and g of x as x approaches positive or negative infinity be equal to the product of the individual limits L1 and L2. So for the limit of c times f of x as x approaches positive or negative infinity, the limit would be c, or the number c, multiplied by the limit of f of x, which is L1. The limit of the ratio f of x all over g of x as x approaches positive infinity, positive or negative infinity, is equal to the ratio of the individual limits L1 and L2, provided that L2 is not equal to 0. The limit of f of x raised to n as x approaches positive or negative infinity be equal to the limit of f of x, which is L1 raised to the exponent n. The limit of the nth root of f of x as x approaches positive or negative infinity is equal to the nth root of the limit of f of x, which is L1, provided that L1 is greater than or equal to 0 when n is even. And the limit of a number c as x approaches positive or negative infinity be equal to c itself. So for the next, if n is even, then the limit of x raised to n as x approaches positive or negative infinity is equal to positive infinity. If n is odd, the limit of x raised to n as x approaches positive infinity is equal to positive infinity. But if x is approaching negative infinity, then the limit of x raised to n is negative infinity. If the limit of 1 all over x raised to n as x approaches positive or negative infinity is equal to 0. So, for example, let's say x is 100, so negative 100. So if x is negative 100, n is 3, then the value of this would be close to 0. So similarly, if the denominator is positive, this value is too small and it's still close to 0. So the limit of f of x all over h of x is, as x approaches positive or negative infinity, is equal to L1 all over positive or negative infinity, which is equal to 0. So remember that, recall that L1 is an element of all real numbers. So all over, if you divide that by a large number, very large number, the value would be approaching 0. Very large or very small number, the value would be approaching 0. So in 11, in this last equation, as x approaches positive infinity can be replaced by x approaches a, and x approaches a from the left and x approaches a from the right. Suppose that both f of x approaches infinity and g of x approaches infinity as x approaches a, then the limit of f of x all over g of x as x approaches a is an indeterminate form of type infinity all over infinity. So infinity all over infinity is not equal to 1. So for the first problem or example, evaluate the limit of x minus 1 minus the square root of x squared minus x all over x minus 1 as x approaches 1 from the right. So you can try direct substitution, but the resulting limit would be 1 minus 1 minus 1 minus 1 all over 1 minus 1, which is 0 over 0. So that is an indeterminate form. We can proceed by rationalizing the numerator, which is done by multiplying the numerator and denominator by the conjugate of x minus 1 minus square root of x squared minus x. So multiplying the numerator and the denominator, we get, and simplifying, we get the limit of the quantity x squared minus 2x plus 1 minus the quantity x squared minus x all over x minus 1 multiplied by x minus 1 plus the square root of x squared minus x as x approaches 1 from the right. So simplifying further, we get a limit of 1 minus x all over x minus 1 multiplied by x minus 1 plus the square root of x squared minus x as x approaches 1 from the right. So the numerator, you can add or combine like or similar terms in the last line of this equation. So you can arrive at this form. So you can also rewrite the numerator as negative x minus 1. So you can cancel x minus 1 from the numerator and the denominator. So the resulting function would be the limit of negative 1 all over x minus 1 plus the square root of x squared minus x as x approaches 1 from the right. So directly substituting 1 to the function, we get negative 1 all over 1 minus 1 plus the square root of 1 minus 1. But since the x approaches 1 from the right, the resulting limit would be negative 1 all over 0 from the right. So since the numerator is negative, the limit of the function would be negative infinity. So the final answer is negative infinity because the limit in the second to the last line is of the form negative 1 all over 0 from the right. So for problem 2, evaluate the limit of the quantity 1 all over 2x minus 3 minus x minus 1 all over 2x cubed minus 3x squared minus 2x plus 3 as x approaches 3 halves from the left. So you can try directly substituting 3 halves to the function. So you would get an indeterminate form of the type 1 all over 0 from the left minus 1 half all over 0 from the left, which is equal to negative infinity minus quantity negative infinity, which is positive infinity minus infinity. So positive infinity minus positive infinity is not equal to 0. So that is an indeterminate form. What we may do is to rewrite the difference as a single rational expression. So this is the given. Rewriting this, we will get the limit of the quantity 1 all over 2x minus 3 minus x minus 1 all over 2x minus 3 times x squared minus 1 as x approaches 3 halves from the left. So rearrange lang yung denominator ng second expression. So evaluating further, we get the limit of x squared minus 1 minus x plus 1 all over 2x minus 3 multiplied by x squared minus 1. So you will just combine these two terms. So you will get this function or expression. So simplifying further, we get the limit of x squared minus x all over quantity 2x minus 3 times x squared minus 1 as x approaches 3 halves from the left. So substituting 3 halves directly to the equation, we get 3 over 4 all over 0 from the left multiplied by 5/4. So since the denominator 0 is being approached from the left or the negative numbers, so the final answer is negative infinity. So you can try using negative values, and in replace of this 0 from the left. So you will get, if you try multiple values, you will notice that the limit would approach negative infinity. So for problem 3, or the last problem, evaluate the limit of x cubed plus the square root of x raised to 4 minus 1 all over the square root of 25 x raised to 6 plus 3x plus 1 as x approaches negative infinity. So if you try directly substituting negative infinity to the function, you'd get negative infinity plus positive infinity all over positive infinity minus infinity. So you can perform operations using that. So recall that the limit of 1 all over x raised to n as x approaches positive or negative infinity is equal to 0. So we must find the greatest power of x in the denominator, which is x raised to 6. So since this is under a radical symbol, we will consider square root of x raised to 6. Multiplying both the numerator and the denominator by 1 all over square root of x raised to 6, we will get the limit of this function, the last line, as x approaches negative infinity. So what we want to happen here is we want expressions to be equal to 0 to simplify the original function. So recall the absolute value function. Square root of x squared is equal to absolute value of x, which is equal to the piecewise function x is if x is greater than or equal to 0, or negative x if x is less than 0. Since it is given in the problem that x approaches negative infinity, we can consider x to be negative. So x cubed is also negative since the exponent is an odd number. So square root of x raised to 6 would be equal to negative x cubed.
So going back to the solution, substituting negative x cubed to square root of x raised to 6, we will get this expression or function. So simplifying further, we get the limit of negative 1 plus the square root of 1 all over x squared minus 1 all over x raised to 6 all over the square root of 25 plus 3 all over x raised to 5 plus 1 over x raised to 6 as x approaches negative infinity. So using the rule mentioned in this slide, which is the limit of 1 all over x raised to n as x approaches positive or negative infinity is equal to 0. So applying that here, we can see that some factors or expressions would be 0. So getting the limit, you will get negative 1 plus the square root of 0 plus 0 all over the square root of 25 plus 0 plus 0. So the final answer would be negative 1/5. So the limit of this original function is 1/5. So that is all for this video. Thank you for listening.